right. I think I'll start. Two things. I was warned that my voice isn't loud enough quite for this room, so I'll try to remember to talk louder. But that is not the ground state. That's an excited state. So if my voice gets quiet, just try somehow to do something to excite me. Let me think. Yeah, thank you everybody for coming back. One of my nightmares is waking up in the middle of the horror movie, The Amazing, Incredible, Shrinking Audience. And, so I appreciate that. There was a little bit of feedback that indirectly made it my way to be careful about how much topology I'm assuming, or homotopy theory I'm assuming people know. And I'm trying to strike a balance between taking too long to explain things and getting a picture up. But as this lecture series moves on, there's going to be less and less homotopy theory in it. I think my next lecture, yeah, there'll just be less and less. My goal in sort of thinking about this Kitaev conjecture is to just try to take lessons from the homotopy theory side and formulate some clear questions about the Hamiltonian lattice model side and vice versa. So I hope, even if you don't know, I certainly don't know the lattice model side very well, but if you don't know one side or the other, I hope there's still something to be learned. So let me, I want to just remind you where I got last time. I want to change my indexing a little bit so it conforms with what Alexei is doing. But last time I introduced this thing called L of Rn, which was some space of invertible gap Hamiltonian lattice models. I'll just say systems on Rn. And so Alexei wrote this as Sn comma base point. So I kind of mean this in a Borel-Moore sense, and I think I'll just define these more or less to be the same thing. But I want to remember the linear structure on Rn. But in terms of thinking of it as a homology theory of some kind, it's really approximating this. And then I defined this thing K Fn. And so this Rn could have been really any metric space X. And I defined K of whatever to be the invertible. Or I'm sorry, these are just the gap Hamiltonian systems, and K was the invertible ones. All right, and then I defined a spectrum, or this Kitaev spectrum, and it comes in several flavors, as Alexei mentioned. I'm just describing the one that doesn't have any extra imposed symmetries, and I'm calling it K, and now I want to re-index this. So I want to say that the nth space in K is this value on Rn. So last time I had an n-1 there, and I want to shift the index so that it conforms. This was an index that was convenient from stating the guess in homotopy theory, but there's a lot of reasons why, the index I used last time, but there's a lot of reasons why this indexing is more convenient for other purposes, one of them being it agrees with the way Alexei was introducing them. All right, so that forms a spectrum. And then there's Kitaev's conjecture. Uh-oh. Which is that this spectrum K, now in this indexing, that spectrum becomes the shift of I C star, or Alexei, an alternative notation, which Alexei was using, is to put a 1 here, or the double suspension of IZ, and sorry, this is maps of M spin, or darn it, this is the spin fixed points. Okay, so that's a conjecture, and I'm also being sloppy or a little vague about what the difference between these two is. I'll try to say that a little bit more clearly today and over the next lectures. But first, before I do that, let's just, I want to just take a minute and think about what this is telling you and why that's a good thing. So what are the path components of Kn? Kn, sorry. What are the path components of that? So those are supposed to be the phases of gapped Hamilton, of invertible gapped Hamiltonian systems on Rm. Okay, so those are n-dimensional Hamiltonian lattice models that have a spectral gap. They're invertible in this sense of stacking up to some kind of local equivalence, which none of which I've made explicit. That's the picture, and the right-hand side provides an answer for us. So let me just. This is mostly a matter of shifting a bunch of indices around, but let me try and do that. So this is pi 0 of the n-fold suspension of this spectrum. That's just a definition of what that's, the relationship between a spectrum and the spaces that constitute the spectrum. And Kitaev's conjecture is that that's pi 0 of the n-fold suspension of the suspension of IC cross to this mapping space, or the spin fixed points of that. There's another version down here that might be a conjecture based on difference hypotheses, and this is the one Alexei was talking about, and this is the one that Alexei described in his talk. So just for convenience, I'll start with this one. Okay, so now I have to shift a bunch of things around. So that's homotopy classes of maps from the 0 sphere into the n+1 fold suspension of IC cross, but then I'm taking the mappings from the spin to that. And that's the same as homotopy. Now I'll just use the exponential isomorphism. That's maps from M spin into sigma n+1 IC cross. And I didn't get around to saying it, but this is just, I gave you this definition of IC cross. Well, let me just say that this is the character group of pi n+1 M spin into C cross. In other words, it's the cobordism invariance, it's the C star valued cobordism invariance of closed n+1 dimensional spin manifolds. All right, maybe.
Excuse me. Here, since you use a spin manifold, so you are talking about a fermionic system. So the phase of
fermionic systems, yeah. And if you wanted to do bosonic, we'd have SMSO here.
Okay.
And if you wanted to do something with time reversal symmetry, you'd have one of the flavors of pin. And if you wanted to do both, that's presumably one of the, that's MO. And my last lecture will be about what's going on in that case.
So do you mean n suspension of K0 or just the full?
So, all right, so I'm using this funny notation. If I have a spectrum E, then E, by that I mean a bunch of spaces, and each one is the loop space of the next. And so it consists of spaces E underline upper N, and that's the loop space of E underline upper N plus 1. And there's a functor from spaces to spectra called the suspension spectrum functor. And then there's another one back. And if I take sigma n of E and I apply this thing called the zero space functor, that goes to the space E, sorry, E underline upper N. So I don't know, there's a lot of, I'm not sure, I'm sorry, this is maybe someplace where you're just gonna have to, I don't mean to be confusing here, I'm trying to use correct notation, but it does take a little bit of processing to go through all these back and forth maneuvers, and maybe that pulls us away from the narrative a little bit. I'm happy to give a tutorial to somebody later if they want to know more about this.
That's the omega.
That says omega infinity, and this one's called sigma infinity. But the main thing I just wanted to say that this locates, this determines all of these fermionic phases, these interacting fermionic phases on Rn as characters of a group that we know. Okay, this is a group that we know. This group is computed by Anderson, Brown, and Peterson in the early 1970s or 60s. So, okay, so that's one thing. I'll say, maybe I'll just take a minute. I don't know, I want to make sure I have enough time, so let me just.
Since you know the group is no, can you give some examples of like what is a zero dimension, 2 dimensions?
Yeah, that's a good point. Yeah, okay, all right. Yeah.
But there's somewhere to find this out.
I actually, to find out what all these groups are?
Yeah, just a lower dimension, like up to 8 dimensions, like that.
Yeah, I can do that. Okay, so before I do that though, let me just, let me just tell you a little bit about the spin bordism groups. Okay, so pi 0 spin bordism Z. So that's just given a 0-dimensional spin manifold, and you just count the number of points according to orientation. Pi 1 spin 1 bordism group is Z mod 2, and that's generated by the two possible spin circles. And pi 2 is also Z mod 2, and the generator is the torus with the non-bounding spin structure. Pi 3 of M spin is 0. Pi 4 of M spin is the integers, and that's given by the index of the Dirac operator. And then pi 5, pi 6, this looks like a KO group, so pi 5 is 0. And pi 7 is 0. And pi 8 of M spin is Z plus Z. One of these is the index of the Dirac operator, and the other is the index of the Dirac operator coupled to the tangent bundle. Okay, so this is a mod 2 index of the Dirac operator. This is also a mod 2 index. So all of these are invariants that you define using K-theory. And spin bordism breaks up into a sum of things that just look like K-theory up until you get to dimension 20. And then in dimension 20, there's a Stiefel-Whitney class that gives you a non-trivial spin invariant that's not describable in terms of K-theory. And so the entire picture is a a very organized collection of K-theory invariants just given by index theory, and then a somewhat random looking collection of mod 2 cohomology invariants. I don't know if that helps. Okay, but all right. So this gives me an opportunity to talk about the difference between the IZ and the IC star. So IZ. So homotopy. So remember, there's this fiber sequence that goes IZ to IC to IC star, and so that gives us a long exact sequence that goes homotopy classes of maps from X into IZ, going to homotopy classes of maps from X into IC star, and this is homotopy classes of maps from X. Oh, I did that wrong. Into IZC. I'm going to put just a suspension here. Then what's coming in is maps from X into sigma m minus 1 IC star. All right, and so this gives me a map. The image of this is homomorphisms from pi m stable of X into C. And this tells you to be in the image of that means those factor through Z. So this is hom of pi m stable of X into Z. So that's surjective. And then this kernel, its image is the torsion in here. So this kernel is technically something like tor or X of some other homotopy group. Well, let me just say this works out to be the character group of the torsion subgroup. So this turns out to be the torsion subgroup in pi minus 1 of X into C cross. So it's like in the universal coefficient sequence. This sequence always splits, and this one separates the integer part out from the torsion part. So that would happen here. So there's no maps from M spin into sigma 3 of IC star, but there is a map into sigma into one of the Z's shifted over. I'm sorry.
So the Z's seem to shift.
Yeah, they shift. That's right. And in terms of, I'll say more about these when I later today when I talk more about how this connects to topological field theories. But okay, let me leave that at that. Okay, so okay. Was there another question?
What is IC? It should be very simple.
Yeah, that's hom. I also shouldn't use the symbol X here. So homotopy class of maps from E into the suspension of IC is hom of pi m E into C. Okay, so is that okay?
Yeah. Thank you.
Okay, all right. Okay. All right, let me go on just a little bit more with this, and it gives us a way to think about this Z and the C star and things like that. So I want to think a little bit more about what it means to give a map from M spin into some suspension IZ again, I want to say this in a different way because these are homomorphisms, but if I want to compute maps into here, I'm supposed to think about a chain complex, right? This is really, I'm really thinking of Z as this chain complex like this. And I want to, if I'm really going to map into this IZ, I want to think of something like a chain complex computing pi m plus 1 and not really, not necessarily a, I did this backwards. What did I do wrong?
You crossed the thought.
I meant to do this. Meant to do that, right? That's the exponential map. So I want to think of it, I want to picture computing the homotopy groups of this as a chain complex so that I could map it into that chain complex. Now, you can't really do it, but there's a model you can make. You can look at a sort of a little groupoid here. You can imagine a groupoid of closed n my m manifolds. And the maps are cobordisms. Okay, so I've got m manifolds and the maps are cobordisms. And I want to think about making this, I want to think about making this, I want to think about regarding this chain complex as a category. So I'm imagining a category there, and I'm thinking of this as a category where the objects are unit complex numbers, and a map between them is another complex number whose exponential gives you their ratio. Okay, so now I can describe, instead of a homomorphism, I can look at this as a functor, and so I have something. In fact, why don't I just call this board m plus 1. So my objects are m manifolds and my morphisms are bordisms, and I want to map it over to this category, which just comes from a chain complex. So this means to every m manifold, I get an object z of m in C cross, and every time I write it as the boundary, and to every m plus 1 manifold, possibly with boundary in C, and the relation is that if, let me say this has n, and that if m is the boundary of n, then z of m is x of z of n, or e to the 2 pi I z of n. Okay, so if n is closed, then e to the 2 pi I n has to be 1. And so it takes values in the integers, and otherwise you get this kind of information. And that's supposed to remind you of something about the way the exponentiated eta invariant and all of that works. And it's also supposed to just foreshadow a way that we're supposed to think of maps from M into here as some kind of topological field theories. Okay. So now, actually, this gives me another opportunity I was looking for to say something in this lecture. I want to just push this a little bit further, and it explains why these Anderson duals appear. And I just want to tell you a little bit about how those came to sort of play the role they do in this kind of field theory. So this goes back to the early 2000s, and I was writing this paper with Singer on the five-brain, on quadratic functions in M theory and topology and things like that. And we were really fascinated with this picture of how you could think about, well, how every every cobordism invariant with values in C star actually could be interpreted as a map of spectra. And then the way these integer valued ones were some kind of field theories, and it gave this picture that once this was a map of spectra, this information kind of went all the way down, and it was a fully extended kind of field theory. So there was this picture in mind that field theories were actually kind of homotopy. Field theories were among other things cobordism invariants, at least invertible ones, and that those could be described by homotopy theoretic means. Now, there was a question that we really kicked around a lot of people did, about what if you tried to kind of move this down further and describe kind of, don't describe this as just a chain complex, but try to go further down beyond the range where this looks like algebra. And this is a place where Stoltz and Peichner really recognized something important. And it was this connection, it was this interpretation of the next couple stages down. And I don't even remember the order of this, but I'm going to mention a conjecture about these IC stars and the role they play. But I don't remember the order, but I just wanted to acknowledge that our thinking about this was really deeply influenced by Peter Teichner and Stefan Stoltz, and Peter was the one that really kind of opened my eyes to how you start to interpret this spectrum as you move down. So I'll get to conjecture about this IC star, and I'll explain it more later. But I just, as long as I was unpacking this picture, I just wanted to take the chance to talk a little bit about some of the influence that led to that, bringing this idea in.
I have some question.
Yeah.
What's the definition of M spin? It's a space. What kind of space?
Okay, so I'll say more about that a little bit later, but M spin is a, all right, this is good. Okay, so M spin is a spectrum. So that means it's some mathematical object that represents both a homology theory and a cohomology theory. So the homology theory, so that is, you take the free abelian group on the set of all K manifolds, K-dimensional spin manifolds, mapping to X. So these are spins. So it's like singular homology, but I'm not using simplices, I'm using closed manifolds. And then you mod out the ones that are boundaries. Boundaries of maps. Okay, so that seems kind of crazy, but miraculously that has a Meyer-Vietoris property in X, and you can calculate this once you've calculated the spin bordism of a point. All right, and there's another one that'll be relevant if I get there today. You can ask what the cohomology refers to. And that's, so let's suppose now X is a smooth manifold. And what you're supposed to imagine is that these classify some kind of families sitting over X where, I'm going to get something backwards. I'm going to get something backwards. So you unfortunately, some symbol becomes negative. So let me say spin minus K of X, where these are, so sitting over the zero simplices is a K manifold. And then I'm going to get this picture backwards. Let me, you know what, I'm sorry, I seem to not be able to straighten this index out on my feet today. I'm just going to say it's smooth manifolds over X moving through cobordisms. But there's a better picture I actually plan to talk about today, and it doesn't, it lines up a little differently with this. So let me just, all right, let me get it. I'll get to that in a second. Okay. So,
What is MK?
I'm sorry,
What is MK? Just
MK is some spin manifold of dimension K.
roughly three, right? Are there any?
But that,
Are they fixed or are they?
it's the set of all maps from all spin K manifolds to X, modulo boundaries, Ezra.
Can I ask a stupid question? Are the orientable manifolds for this theory the spin manifolds?
Yeah.
Okay.
Yeah. Okay, all right, let's see. So, let me try to connect to a picture here. Okay, all right, I was looking for a way into this, and I'm going to try it. Let me stick with this picture and move a little bit further down in this IZ. Okay, so I want to think of. So I imagine that this bordism category in some small the homotopy type of this in some small range of dimensions was modeled by a little category of manifolds moving through bordisms, and we can try to extend those a little bit further. And so let's first talk about extending this a little bit further. So let's look at the homotopy groups of sigma m plus 1. Actually, I guess maybe I better I'm going to put a 2 here now because that's what comes up in Alexei's.
We're sort of discussing and bothering Ezra while we discuss. What is the difference between a map to X and a map over X?
It is a map, but one of them is a map of a manifold to the X, and the other is trying to be a fiber bundle of manifolds, except that the fibers are moving through cobordisms.
I think the term moving through cobordism is somehow confusing.
Okay.
Like, relation uses something like the fiber-wise bordism, right?
So I would have thought, but I guess I'm wrong, that if X is a smooth manifold, then to move through cobordism just means to have a proper map over X, and as opposed to its.
But so there's
This is clearly wrong.
like a relative.
I suggest that we take this offline, that we do this later, all right? I just, or I guess I have like a definite plan for tomorrow's talk, and I want to get done with today's talk, but I have some questions I want to get to today. But let me just, maybe I can say something. Look, all right, maybe I can answer your question. Okay, so.
Maybe it's just helpful to say that in the second case, the dimension of the thing mapping is the dimension of X plus K and not K.
But that just makes it look like it's just the same thing by a degree shift. That's clearly not the right answer. So
I'm looking at, look, I'm supposed to see, actually, let's just talk, I'll explain it in the common room or something after. All right. Let me just move on a little bit. Okay. So here we were playing around with the difference between the unit complex number and C, and I want to give you a different description of this IZ. So again, I'll stick this into dimension m plus 2, and I want to tell you what the homotopy groups are. So pi m plus 2 is Z, pi m plus 1 is 0, and pi m is Z mod 2, and then it goes down. But I just want to stop here. Okay, so I want to just look at this much, and I'm not going to worry about this index m at this point. So I just, instead of modeling Z or C to C star, I want to model this. And this, whatever this is, it has more homotopy theoretic content. It's not just given by a chain complex of abelians. And what this is modeled by, it's modeled by the category of superlines. So it's Z2 graded one-dimensional vector spaces, isomorphisms, and it has the symmetric monoidal structure of tensor product. And so it's that symmetric monoidal structure that connects this Z2 to this Z and makes it not have this linear structure. And so I can also think of a map from M spin into sigma n plus 1 iz as a functor from m plus 2, as a functor from the category of bordism, the two category of the two category of whose objects are spin M manifolds, whose one morphisms are cobordisms, and whose two morphisms are manifolds with corners. And I can think of, so a map like this, I could restrict to this category instead of that one. And then that gives me to every M-dimensional spin manifold a superline or a vector space. One-dimensional supervector space to every cobordism morphism between a map between those, and to every, yeah, I'll leave it at that. It's a functor to that category, and then so I can recover. In principle, I can recover this integer invariant or the C star invariant from this line bundle. So if I imagine I have an M plus 1 manifold and I think of it in some way as a family of M manifolds that possibly changes topology as it moves through a cobordism, I can take this line bundle and look at the holonomy as I go around that family. And there's something else I could do to get an integer out of it. All right, and this is the thing that's germane to the Kitaev, Alexei's conjecture, at least from the point of view of topology. So remember, Kitaev's conjecture was that we have this, that K is equivalent to maps from IZ from sigma 2 okay, and so in particular, K of SM that corresponds to sigma M plus 2 IZ M spin. Or if I rewrite that, that's maps from spin bordism into sigma M plus 2 IZ. All right, and that's the thing we talked about here. So this gives me, this side corresponds to some sort of lattice model. Oh, good, I have all these colors here. So I have some lattice, some site in here, and then some really cool Hamiltonian describing electronic properties of this system. And then that's supposed to give me something that associates to every M-dimensional spin manifold a supervector space, a line inside supervector spaces. And what's sort of physically, what is this supposed to be? So what it's supposed to be is that, so this is also something I learned from Alexei, that you want to think of this lattice model as describing a kind of M-dimensional material. And you want to think of your spin manifold as you want to make a dress out of that material or something. Your spin manifold is some shape, and you want to manufacture that shape out of that material. So how do you manufacture a shape? Well, you break it into regions, right? And so that's a few regions or something. And then I guess I'm going to have 4 regions if I do that. And then I build these out of this material. I cut my regions out of this material, and then I sew them together to make this picture. So let's make the sewn picture look like I riveted it to put it together here. Is it 2? Sorry. I used to be able to think on my feet, but I don't anymore. Yeah, that's 2 regions. Okay, anyway, or whatever, you know, maybe these were lattices and they had some Hamiltonian in them, and I'm supposed to put that in here. And so the picture is supposed to be, you have this material type given by this Hamiltonian lattice system. You put the system on your manifold, and then you calculate the ground state. That ground state is supposed to be one-dimensional because it was invertible, and that's this superline. And that's very functorial in sort of moving manifolds and families, and you calculate the spin bordism invariant from that. So, sorry?
What are the 2 regions again?
What are the 2 what?
Regions.
They're just, let's see. I cut this like that. That gave me 2 tubes, and I cut it open. So this gets glued together by, these are glued together, and then you know, something like this. There's something like that. Okay. So, all right. So this is a heuristic. It's more than a heuristic. You can really go with this. This is really how this is supposed to work. But it leads to 2 questions that I want to sort of throw back to the Hamiltonian side that I don't understand. 2 things that are very natural to the picture and topology, but I don't understand how they work over on the lattice model side. So let me put one of them here. So question 1. I mean, how do I? So if I want to say, so let me go back. Let me just draw this picture again. So I have some manifold here, okay? Some piece of some manifold here, and I've got, and I'm trying to build it out of a material type here. So this is maybe some infinite dimensional material type, and I've got some Hamiltonian, which I'm indicating by sort of electrons bouncing around. And now I have something sitting on this manifold, and I want to recognize that the material I use to make this is that material. And so I'm going to look locally here, and I've got some little system here, and I somehow need to know that that material is the same as this one. And I don't really know how to meaningfully do that. So the question is, so another way of saying it is, this is something very local, and this is, I mean, when we want a phase associated to a lattice system, we're really supposed to imagine that that system is scaling under some sort of renormalization flow, and that we're really looking at some IR limit of these models. And it's the same here, and we're somehow supposed to imagine I have some system of these that's getting finer and finer and finer, and that I'm somehow in the aggregate, I'm supposed to be able to recognize what's happening locally here with something over here. So I don't know, this is a vague question, but I want to say, how do you recognize the Hamiltonian system on a manifold M as being a given one on, say, Rm. We know some ways to do it. If you wrote down the toric code here, you sort of know how to say in terms of Z2 bundles and things that you've put the toric code on a manifold. But if you give me just some random, I know how to do it in all these, for the AKLT model, for the Kitaev wire, for all these models, we sort of, in principle, know what to do. But if you just give me a random invertible phase here, given in terms of a Hamiltonian system, I don't really know how to put it on an arbitrary manifold. And I'll try to. So this is one question I'd like to kind of bend what we know about lattice models to sort of give, at least change this question or give some sort of an answer to it. Okay, so all right. Not sure how.
Yeah, I have a question here.
Yeah, okay.
You have this map from particular manifold to this some line, a line which is like a one-state function.
Yeah, yeah,
But if you deform from a manifold,
yeah.
for moduli space, then you make it
A line
line
bundle.
bundle on
Yeah,
moduli space.
yeah.
Whether it's a line bundle by a crucial rule.
Yeah, so for example, if I had that line bundle, I might look at its first Chern class, right? I might get a number out of that if it was a 2-parameter family. And that number would be the Z 2 dimensions up. So when I use IZ, I have the sort of kind of system that can locate an integer quantum Hall effect type of integer. Yeah, so that's
Including the setup.
yeah, included in that setup. Yeah, that. Okay, I want to put another question up, and I don't have time to introduce all the apparatus. Let me just see. All right. I'm going to state a question, skipping over a whole bunch of apparatus. So what I was really planning to do was talk about the cobordism hypothesis and how we might conceive of a not necessarily invertible version of Alexi's conjecture. But maybe I can just say a little bit about it. So if we imagine that we're taking some manifold and we've got a sewing pattern, we have some sewing pattern and we're going to sew edges together to build a bigger manifold. I have to think about how I go from this phase to maybe another phase, maybe the same phase, and I have to think about how I connect between them. And so in the language of the cobordism hypothesis and in the language of kind of phases of field theories, the sewing instructions form a domain wall. And when I have 2 domain walls coming together, they're a defect. And so there's this whole hierarchy of structures that we would need to actually sew these things together and put a phase on a manifold. So I'm sorry, I'm just going to state a question and then people can talk to me after, or if I can fit a more expanded version into one of my next talks, I will, but I'll try. But let me just put up a different question. So let's go back to this L, which were these gapped phases, and I want to make L of Rn. Rm. Can we make this? Can we make these into the objects? So question, can these be made into the objects of an infinity n category with duals? Okay, so an object would be, so the objects would be like a phase on Rn. Okay, but it's some phase I'm zooming out of. And the tensor unit would just be the empty phase. If I wanted to talk about morphisms from the unit, one morphism from the unit to something else, I'd have some boundary, a phase, I'd have some Hamiltonian system with a boundary. And I'm imagining I'm going to some IR limit of that. Or more generally, I could have two different phases here, and I'm looking at a domain wall between them. And I could go on. So we know again for all the examples like the Majorana chain or the toric code, we know also what kind of boundary conditions we allow. And I think I don't know, I'm not looking back at Alexei now because this might be obviously not doable, but a natural question from the way this fits into topology is that the theorem that the invertible objects form a spectrum might be just the invertible part of a more general theorem that assembles these things into an infinity n category with duals. Okay, so that's another question I don't know the answer to, but it would help I mean, these come from examining what this conjecture really means on the topology side, and then going back and asking, well, does this structure appear over on the analysis on the Hamiltonian lattice side? So there's another
Can I ask a
oh,
question?
yeah.
You had a tensor product on L.
Yeah.
So is this infinity n category meant to have an extra?
It's a symmetric monoidal infinity in
Symmetric
category.
monoidal.
Yeah, thank you. So a symmetric monoidal. And now Alexei made a conjecture about what the invertible part was, which was this Anderson dual in spin bordism. And there's maybe I can't. There's it's not so easy to formulate the analog of his guess in the not necessarily invertible case. So maybe I think there's not time here. I'll try and pick this question up again. Yeah, I think I'll pick this up again at the beginning of my next talk because there's more to this question. It's not so easy to see how to formulate an analog of Alexei's conjecture about what this is in the invertible case, but there are many possibilities, and I think in the Hamiltonian lattice side, there might be some way of getting guidance into what the reasonable conjecture here should be. Let me just think if that was where I wanted to end. I think I'll stop there. So I'll finish. I'll state the other part of this next time.